All right, so today we're going to work on a LeetCode problem. However, I cannot get myself to code in this environment because I like running my code really quickly and it honestly gives me a headache. All right, so this is the question we're going to do. And Queens, I believe it uses backtracking. I saw some performance engineering lecture from MIT. That class is really cool, although it's kind of hard. I wasn't able to take it in undergrad, so I'm trying to take it now. And I kind of heard a solution and I just was watching it while eating, and I decided today I would try to actually do it myself. I'm going to start the solution off with a list implementation, although I was trying to do it with bits. I couldn't do the bits in Python. It was an interesting switch from C to Python. I'm not exactly sure what's happening here. There's something about masking that I think I need to do, but before that, I'm gonna just do it with a list and then we'll switch to bits after because that's what I want to get better at. Obviously, it shouldn't be in Python, it should be in C. I'm learning C, but I don't want to do this video in C just yet. All right, so this is the end queens problem. If you haven't heard about it, it's this idea that you have a chessboard and you want to put queens on it and they can't effectively attack each other. So you basically want queens to not have each other in the sight lines. The MIT class kind of created some really interesting representational ways of doing this. I believe the algorithm they use is backtracking. I don't really formally know what backtracking is, but we'll see if it works. And given an integer, return all distinct solutions for the end queens puzzle. I see. So this is all the solutions, which would effectively mean if you find a solution, you would want to keep going. I'm not going to do that. I'm just going to get one queen. Yeah, I think we could probably find all the solutions, but I don't want to think about that. I just want to find one. So the way that the algorithm kind of seemed to be done, it was like you check this point. So you're here and effectively you have a queen proposal. So what a queen proposal is like, hey, I want to put a queen in this column and then in this row. The row is going to be done through the backtracking, so we don't have to save information. How do you check to see if you can do a queen of this column? Well, you want to set that bit effectively to 1 and check to see if it kind of conflicts with anything inside the actual existing board. So in this case, and I'm going to code here because honestly it just feels better, and we're going to have queens. And I like running early tests, but I find this environment to not really be conducive to do that. So effectively, we're gonna have the first queen and we want to set up our representation of the board. In this case, we're gonna use a list, but you probably should use bits. I just haven't figured out exactly, and I don't want to know too much about the problem's implementation before I start. I think most of the videos you see, someone spent like 6 hours, they show it to you in 20 minutes and you feel a little worse about yourself. This is me doing it effectively after watching a lecture of someone doing it in C and then waiting like effectively like 1 full day, and now I'm going to try it myself. All right, so the board is going to equal, we're going to make it zeros times n. And that's great. We're going to there's effectively a diagonal, and that's actually 0 times, and I'm going to show you why after I type the magical equation. I already had that multiplication in there. Times, and then minus 1. And then we have diagonal L, and then diagonal R. Okay, cool. So why is this our representation? So board N is pretty straightforward, right? If you're gonna check to see if a value is the right one, you want to say like a proposed queen is gonna equal proposed column, let's say, equals, I don't know, 2, right? Yeah, 2 will be fine. We'll say N is 4. So then here we'll have def test of 4, and then we'll just do assert first queen 4 and equals some setup. I think For 4, we can just do the index of it. I think it's like, it has to be horses, so we could do like, actually we'll just grab it from here. So it's, yeah, 2, 0, and then kind of like an inverse horse setup. So 3, 3, and then 1. And this is just a notation. 2 is 0, 1, 2, 0, and then 0, 1, 2, 3, and then 0, 1. Right? Okay, cool. It may not be that case that we get that, so we'll just say in, and then we'll see if the return is of that form. And for now, we'll have a set of, oh shit. We'll have for now a set of I think this works. Not 100% sure, but we'll do. I don't really care for Python syntax right now. All right, so why are these diagonals that? Okay, so for columns, simple enough. For diagonals, you have to think of diagonals in this structure. So we're just numbering them, and then we're just making sure to increment. And it's actually really nice that you can actually calculate this really quickly. So for a diagonal, you have the first one, second one, third one, fourth one, fifth one, sixth one, seventh one. Right? It's 0 index. This was like my way of trying to show you the 0 index. So you have 7, 4 by 4 minus 1. And you can think of it as the first element is going to get rid of 1, and you basically get for each row one of those, right? But you got rid of half, like more than half. You got rid of the top half of this triangle. So you basically need the bottom half of that triangle. So whatever, we get the first half of this, and you kind of get this idea that it goes up to 3, and then there's a repeated version of that, and then you have 1. So you're basically double counting the first up to n minus 1, double counting up to n minus 1, and then you have this diagonal. And there's some interesting squaring combination stuff that I couldn't reproduce right here, but trust me, it works, and it's pretty fun. But we're not going to use it today anyway. Okay, cool. So let's go back to the more fun place. So here we have proposed column is 2. And then what does this proposed column is 2 mean? Technically, it could just be a bit, but in this case, we're just saying we're going to add a 1 to that. So for the check, we would say board 2 not equals, sorry, this is like keyboard stuff, not equals 1, right? So if board proposed column not equals 1, then we'll have a valid, right? So valid column equals that. Cool. And then for now, we're just going to print valid call, and we're going to run our tests. I don't even know if I have PyTest. I usually just have my tests in there. Oh, I see. I just nuked my computer. I needed to like not tell you my full name, so I ended up making Eddie Studies. But in doing so, I basically ruined it for this video, but whatever. Okay, so we source that. That's a weird print. Yeah, I guess it worked. Why did it print that? That's so weird. I feel like that's wrong. Queens. Oh, I see. Maybe I need a... that's what it is. Okay, cool. Sorry, I'm trying to set everything up here. So valid. Oh, yeah, cool. So we're pretty much ready to see this little test. Okay, cool. Valid queens, prints. The print doesn't come out unless I do -s. Sorry, I'm showing you my full process with nothing different. Okay, cool. True. So valid queen is true. Great. And just to set up a bit better, we're gonna split this. I'm in Tmux, right? So, oh, my key. Oh no, it's here. Oh, it's not control anymore. Yeah, I really messed up my computer. I'll fix it another day. For now, I'll just deal with this. Okay, so I need to do control B and then left arrow. Sorry, I had Tmux bindings, but by nuking my home directory now, I lost all my files. Cool. First queen here, valid call, works out. Okay, cool. So valid call, and then it's actually really interesting. So valid diag left is what you would think it's hard to calculate, and it is, but it's actually proposed row. And honestly, we could do like p call, p row, and we'll just say this is 1 for now to show an example, and then we'll just do a let's see if I can do it s. Okay, that's worked. I don't usually use us. Yeah, whatever. That worked. Okay, cool. So we have the p call here, and then in this case, it's not so much that equals 1. So in this case, the valid diagonal left is if diagonal L of diagonal L of, and in this case, it's p call plus p row. And I'm going to show you that over here because it's a little easier to show. So here, right, if you're at 0, 0, you're at 0. If you're at 0, 1, you're at 1. If you're at 1, 0, you're at 1. And kind of the same thing approaches. So 6 is 3 plus 3. So that kind of shows you. So it's sort of this way of indexing that kind of works out perfectly. And that's for the left. So diagonal equals 1. And we can actually just get rid of this equals if diagonal, so this is not right, it's just like that diagonal is empty. And then the same thing happens for right, except you can think of it as right starts here. So then you just add the -1. So then here it's minus, and there's a few ways of doing it. I can subtract both, or I can put them in a parentheses. This is probably not the safest way to do it, but that's how I'm gonna do it. And then we're gonna have p call. We're gonna have 2 times n minus 1. Yeah. So this is like effectively saying the diagonal is on the opposite side. So now we have our 3 checks. So it's a valid call, it's a valid diagonal, it's a valid diag R. So then in this case, we're trying to make it for the 0, 0. So for 1n equals 1. And then we're going to expand it to support like the iterative process. So then if valid call, right? And then in this case, this would be 0, 0 for the n equals 1 case. And then we basically want to return 1 or 0, right? Actually, we want to return true. So in this case, we're going to return valid valid call and valid diag L and valid diag R. So we'll just do an if here because we'll use that later. If everything is valid, then I don't even know if you can do this. Sometimes I think you can. And then let's just make sure. And then we're going to return what is our setup? I'm going to return 1 or just 0, I guess. Yeah, we're just going to return 0. So then we're going to add a test for that. Test 1 and then first queen of 1 in set. There's only 1, so we can just do an equals and 1. I think we have to put a comma here. All right, let's see. If I test this, yeah, man. Queens, we have 1 test passing. Cool. So we have that first check. So we're able to do 1. Now let's see if we can get 4 to work. Okay, so for 4, what we're going to do for 4 is we're going to have this P call and P row. We're going to iterate through the row. So we need P call equals, and we're going to set this to be 0 times n. So this is similar to board, but now instead of having P call, we have P calls I. Okay, P calls I, P calls I. Okay, so that's our proposed. This should work exactly the way that it worked previously, which we could just check. I can't run PyTest in here, and it honestly bothers me. I'm going to fix that. I is not defined. Okay. So let's do that. For I in range n, we're just going to keep that there, and this will never print. So we'll just run it. Cool. So we have our test passing for 1. So now we just need to see what we do in the case that it's valid and the case that it's invalid. Okay, so if it's valid, then we're going to increments. What do we increment? So here we know we want to keep the P calls I where it is if it's valid, because that is going to be where we go in the next round to then remove it and then try to find another solution. So then in that case, we want to increment. So then in this case, it won't be a for loop. It'll be a while P row is less than n. And P row is greater than -1. So basically those are our end conditions. If it's -1, there is no solution. If it is n, we found a solution. So then in that case, here we want to do P row plus equals 1. Because we basically figured out this row. So we're going to go to the next row. And what else do we need to do? We also need to update the table. So then in this case, we're going to do board P calls I equals 1, right? And then diagonal. Oh, I really should just use diag. P calls I plus P row equals 1, and this one's pretty similar. And we can do some tricks later to make this faster. And we'll just put this in parentheses like we did before. And then p row. Okay, so we update the board. We say we're good. We go to p row. And then in this case, we have okay, so then here, if we get to here, so if p row equals n, then what we're going to do is we're going to return tuple of board. Is that right? So we're going to return we're going to return, and then in each of those elements we're going to have a 1. Right now is this assuming the board is flat? No. We're not saving the current column and row. We could backtrack it from our diag and board, but that seems a little silly. So what we can do for now is we're setting up here, it's the columns. So let's make this board calls. So much faster than the other way. Okay. And then here we want in board calls. For this check, if board calls equals 0. If board calls equals 0. And then here we're going to make board calls equals I, which then allows us to return tuple board calls. Which kind of circularly makes it so that we probably could just make this board. This is kind of antithetical to the bit solution. I don't even know, this is the jankiest thing I've ever done, but I just really want to show you it from a position of not actually knowing what I'm doing. I think it's important. All right, so p row plus equals 1. Okay, so this is the positive case, and we can test this on something, but let's add a negative case. So for the negative case, there's a few things that could go wrong, but do we need to know everything? No. So the negative case just says that there is a conflict. There's a conflict with the setting. So if we go back to this, I'm trying to put a thing. I came up with this, and then I came here, and it was like, I can't do it. Then it came here, and it's like, I can't do it. And then it tried here. Okay, so it has one here, one here. And then it said, okay, cool, here. And it has one here and one here, which means it can't do here, any of this. So then it pops this guy off. And it tries to find it here. So now you have one here and one here. And it tries to make this next one. And it can't here, but then it can't anywhere else. So then it pops this one off. It can't fix this one, so now it has to pop this one off, and it goes here. And basically we're just trying to make sure that we backtrack to fix it so that it gets a configuration. So in this case, we're going to try to implement that. So effectively, the way that algorithm works is we try to add this guy. So let's say we added this one. We tried to add this one. It doesn't work. We try to add this guy, and nothing works. Nothing works effectively means we got to the end of the effectively the row. So then in that case, that means p calls I plus 1 equals n. So next p calls. All right. So if p calls plus 1 equals n, then we need to do something different. So in this case, p calls plus 1 equals n. That means we basically ran into a configuration where if we were to increment forward, we would actually no longer be able to solve this problem. So then in that case, we need to reset the current index to be 0. So then p calls I equals 0. P calls I minus 1. So if it's n, we can assume p calls I minus 1 is in the system. And what we want to do here is we want to increment this, because actually, yeah, so here we want to increment this. Okay, we want to, okay, so we're here, we put this one, so let's just represent this. So we have 1 0 0 0 0 0 1 0 0 0 0 0. Crap. So we reset this one to be here. We go to this one and we pop it. And since we're here, we need to go here and then try again. So then here we have, yeah, I think that's it. So we need to go to the next previous one, and then I think we need to increment it. So I guess if p calls I minus 1 plus 1, so if that's also at an end, we can kind of like skip. Then I guess we pop that one too. So we set that to 0. And then I don't want to do that. Okay, so let's handle this a little bit more, the base case in the front. So here we're going to have if p calls equals n. We don't need to do that. We can do it at the front. Okay, cool. So let's just get this if. We just want to like isolate everything. So here we basically want to do, what do we need to do here? So here at the end, we need to effectively reset the current one to 0, because there is no solution here. We're gonna have to start from scratch here if that is already at the end. And I minus equals 1. Okay. And p calls, let's see here, p calls I minus 1 plus equals 1. So we just want to increment, we want to make sure we're trying to make a decision and board board minus 1 equals 0. Diagonal. Let's just switch all the diagonals. L. Okay, so we gotta make sure we remove this diag too. So diag L I minus 1 plus okay. I minus 1 plus cos I minus 1 equals 0. And then here it's effectively this minus for the R1. We're basically saying your next available option is the next one. And you don't have a item in that row. So then here at the beginning, we will handle the I'm in an invalid state from the start. If P calls, all right, first off, I minus equals 1 at the end of this. If P calls I n, so in this case, we need to do this kind of like pop the previous. So let's turn that into a function. What does it need? So it needs I, it needs P calls, it needs board, it needs diag L, and diag R. You could probably not pass all of this in, but I like kind of like treating it like it's almost functional for some reason. It just feels better that way. Okay. And go to the next thing. Forget all this stuff. We don't care if it's valid, if it's too big. Could it be too small? So, could it be too small? No, it can't. It only increments, right? So that's fine. Okay. So then that calls if P calls plus 1 equals this. Remove previous. I plus equals 1. If it's at the end, remove previous. So then do we just increment it? Right? Because then I'll just go to the beginning. So remove previous is saying p calls I is 0, so we're setting the current one to 0, setting the previous one to 1, setting the board at that previous element to 0, setting the diagonal of that previous element to 0, the diagonal at that right to 0. So we're zeroing out everything we know. And then we're decrementing I. So in the next case, okay, cool. So when we get to the beginning, then it'll move forward and it'll just try everything again. Okay, this is interesting. I don't know if it'll pass, but we'll see. Okay. Okay. Okay, let me just get rid of the tuple thing. Oh, I can just say tuple. I wonder if this will work. Yeah, that's what I thought. So I'm just gonna switch this to not be a tuple because Python is silly. Just board. And then here's just here. I'm not gonna do anything fancy. We can't do set, but we can. Yeah, we can't do set. So we'll just say equals equals, and if it fails, we'll just, whatever it converges to, we'll just switch it with the right answer. Cool, assert 0 equals equals 1. That's silly. And then assert 0, 0, 0. Oh, okay, we're returning 0. Okay, cool. And what should it be? It should be 0, right? Because that's our setup. Okay, cool. So first test pass, and then now we want to see. Honestly, I want to see how it runs. See where it runs. Okay, so we have this helper function, and let's see. So I always do this. This is my favorite way to debug. It's just nicer than most ways. And the best part about it is, honestly, whoever uses this, remove from doc. Okay, cool. So let's just make sure everything looks proper. Len board. Let's do it. Diag L, diag R. That's true. So that's a good calculation. And then P row. Okay. Okay. So let's print everything. So board is currently, diag L is currently, diag R is currently. Board, diag L, diag R. Board is weird. Why is it 1 there? Okay, that's weird. Okay, P row. Okay, that worked. Okay, so here we have this. We're gonna implement this. So what is valid call? Valid diag. Valid diag R. Perfect. Oh yeah, we set those to 1 when we're there. Perfect. That makes sense. Okay. So then we're saying board is updated equals I. Oh, it should not equal I. We're going to make it equal. I see. If it's equaling I, and that's actually okay, because we're saying the first element is 0. But we're kind of convoluting 0. So we're going to increment everything, and then, yeah, we're going to increment everything so that 0 is not indexed there. I don't like 0 being there. So here we're going to make board equals I plus 1. This just fixes some 0 indexing, and technically we can do x minus 1 for x in board, just to keep everything avoiding 0 where possible. First test is fine. Let's fix the we don't really care too much about the beginning anymore, so we're gonna move this to here so we can see some of that control logic. All right, so I is there, p row is fine, if p calls valid, all the valids. This is the first one, we don't have to check it again. All right, so now board has 1 in that position. Huh, interesting. Did I? Okay, so we got some negative 1s. Okay, so let's just do test 4 now. I forgot what the file says. And Queens. Cool. So here, we're here. So we the same p row is 1, board, diag L, diag R. So is this accurate? So 1, 1, and then it's saying this one, which is, it's not actually true, is it? Oh, it's saying, so it's saying this. I don't know if that's accurate. So diag R might be broken. What would be the diagonal there? So I think it might be okay. It might be idempotently okay, but like it might be like wrong in a consistent way, so it'll be fine. Oh, okay. So it's saying interesting. What is I? I didn't increment I, did I? Okay, so let's just do that. Okay, cool. Better. We're getting all -1, which is not great, but we will figure that out. Okay, so honestly, sometimes you want to move your this somewhere else. So I feel like this is the interesting place to have it. And here, we want to know when we remove something, and we want to know when we added something, and when we're like, nope. Okay, let's see. All right, so in this case, let's be arrow and please, so we can just have the code here. This is kind of why I don't like being in the other system. Control B arrow. I need to make that my actual key bindings later. All right, so board. So we are inside, which is fine. But now what do we want? We want P row. Ooh, P row. Ooh. That's the problem. We have this old I, but we're not actually using it. Okay. Let's, so I am using this screen mostly as a cat, so we can just do that. And then Vim Queens, so it doesn't bother me too much. Okay, so we need to replace this I usage because we switched it, and this is mostly because this is kind of like in the middle. The what 60? Yeah, cool. So we're gonna move this guy out. Shift that. Okay. And this is because it's using I in here, but that's fine. And then here we are using P row. I like doing this when I have a thing, because this is like what we're kind of going over here. So here I is just wrong. It's P row in every instance. Yes. It's the type of bug you get when you try to code a little fast. Oh my god, I have no patience. Okay, cool. And then let's just probably test this. Okay. So is board correct? Is P calls correct? P calls did not get incremented because it worked. Cool. And then we want diag L and diag R. Diag L, R. I think what I did is I ended up making it so it's like diagonals are from here that way, and then the others are from here that way. So they are technically the same orientation, just mirrored. It works. Okay, so we're gonna go to the next iteration. So where are we? So we're at board P call. It says this is a valid board. So why is this valid board? Okay, we're setting up here. What's P row? Valid call. Valid diag L. Valid diag R. Okay, it feels off, but 1, 2, but they're not valid. My diag is wrong. Yeah, my diag is wrong. So, okay, so if you're on the... So if this is the way I have diag right, this is the way I want diag. So we want it to be... the top left corner. I think we need to shift it with a mod. Okay, so this diag right is wrong. So this one I think is fine. So we just have like that. So then we need, so this is 0, 1, 2, 3, 4, 5, 6. So then we need 0, 1, 2, 3, 4, 5, 6. So then this would be 3. Yeah, that's what I thought. So then it's n minus 1. And then when we do 0, 0, it is just n minus 1. And then when we do 0, 1, if we move up in the row, it moves down. So then it's this minus the row minus the columns. Oh my god, minus the columns. But plus the rows. Is that right? So if we have a row that makes it, yeah, I think it's 0 minus the column plus the rows. Is that right? So then how would that work? Let me go here. So what we want is 3, 2, 1, 0, 2, 1, 0. Oh, this is 1. Okay, so this is 0. If we go up columns, we subtract. And we start at 3. Go up column, up column, up column. And then the others increment. Yes, so we start at 3. And then if we go up a column, we decrement. If we go, I think it's this. Okay. So that's kind of how I do it. Lord diag R diag L. Nothing changed. Oh, I switched remove previous, but not. So this is just telling you I'm just doing this like a caveman. I should be doing this more holistically. So let's see, that, and then just I. Just trying to quickly go through. Name I. Where's I there? I don't see I there. Big Oz, B row. Oh. Cool. Yeah, cool. So we're incrementing, but it looks like this function is not doing what it's supposed to, and this function might not be doing what it's supposed to. So I need to figure that out. Okay, so let's focus on this guy. Honestly, I feel like I should start isolating stuff, but for now we're not. Okay, so let's see if we can give a. Actually, yeah, let's do that. Dev test, remove previous. Let's start isolating it. Wow, I have no configurations. All right, so let's give it a board. So in this case, we need to remove previous. And we want to remove previous. It's going to be index 1. So we're trying to add the second row. And our p calls is going to be 0, 1. Our board is going to be 1, 0. Let's make this 2. P calls 2. So that this is indexed wrong on board, and then diag is gonna be 1, 0, 0, and then the other one's gonna be 0, 1, 0. Okay. And then we're gonna assert, remove previous. What does it return? Okay, it's just a modifier. So that means we need to actually set, what are we going to modify? So, God, it's like a very mutation heavy thing. So, p calls equals 0, 2, p board equals 1, 0, diag L equals 1, 0, 0, diag R equals 0, 0. Okay, and then we just want to call that, and then we want to assert p calls 1 equals 0. We want to assert board 0 equals 0. Assert diag L 0, 0. Assert diag R1 equals 0. Yeah, because we're just going to remove it. Queens, and then 2. This is, you can't do 2. So 2 equals 0. Okay, so let's see. So p calls. So we get an I input. So we got 1 as input, and p calls is I equals 0. Oh. Cool. That fixed that. And then let's see. Sorry, I don't really talk too much sometimes when I'm doing this. I don't know. This is like the natural way of doing it. I mean, you can try to be performative for an interview, but I just feel like we just need to kind of go back to being normal humans. All right. So here we have board. See, that's why I'm confused. Okay, so something's off with this check for is valid. So that is bad on the diagonal. So we need to check that. So here we have board. Okay. Valid diagonal. It's an empty board. Okay. So it's saying it's gonna go 1-1, but valid diag R shouldn't have passed. So what's our valid diag R code? Let's see. Valid diag, not diag. Oh, it's diag. That's so funny. Okay. Perfect. Okay. Alright, this looks promising. Let's see if it works. I always do this funny style because basically it throws a rough error. Like it doesn't like it when you have the numbers in that style. So I basically break builds so I can never check in by mistake import PDB. And then if you have linting, automatically it'll catch that and it'll be like, hey, like you failed your lint. So I always import PDB with that set trace. Okay, so it looks like we are making progress, but still not perfect. So what I want to do is here, I want to check to see all the valids. And then I want to also see all the removals. I think these are the two places that I can kind of get an idea where we're going wrong. So here we have a valid. So we have p row, p calls, p row. Just making a simple both together. So we can just see it. Okay, so see, and then let's see. You know what we can do? This is just for debugging, but I like doing it sometimes. Actions equals this, and then we'll do actions, and then here we'll say actions.append, remove I minus 1 because I equals 0. Remove, we got I reached end, remove one, removed, and then reach end for I removed I minus 1 board diag L diag R. Okay, this is kind of going to be a humongous list, but I think it'll give us the information we need to see what actions are being done. And then we just need to do here actions.append added IP calls I board board dag R dag L. This will just be a nice little printout to debug. So we can just say actions here. Let's remove this. Let's just get rid of that I. So we have actions. We added 0, 0. So actions, we added 0, 0. We added 1, 2. Okay. Actions, we reached end 4, 2, removed 1. So what does that say? So we have 1, 0, 2, 0. 1, 0, 2, 0. I don't see the removal. Okay, so removal on board. Okay, so removed, and we have okay. So here, when we do p row, we're fine, but when we do board, we need to do tuple. This is like an expensive debug, but we'll remove it. Okay, and then here, same deal. You can already see that removal might not be working as intended. Okay, p row equals p calls. The current calls we set to 0. We never set a value in it. Yeah, so we go to the previous one. Oh wait, is it board? We don't know if we have the previous. Oh yeah, that's right. Yeah. So we added. I see. I see. So I think what's happening is that this is wrong. +1. Okay, so it's so for queens, I believe it's something like I can just run it actually with the wrong. It's some sort of sequence of. Um, it's probably wrong, but whatever. I got an answer. Let me just verify this is correct. It's a little funny to say I got an answer, but I'm just taking my answer and assuming it's correct. But it seems promising. I think for me to accept this as an answer, I need to see it. So let's make a viz. So here we're having, these are the columns, and then in it, it's the row. So I'm just gonna set it to be circles and cues. So we're gonna make it board equals for I in range and for j in range n. And then, actually no, so we're gonna do region. Okay, cool. So we have a new set of zeros for each of these, and then we're just gonna do for, so this is the row for the call. So this is the row. So then for I row j row enumerate first queen and then we're saying board row j so right, so it's column 1 0 equals 1, and then for row in board print for row. Okay, Python means here we are on Python, and then okay, it's not the perfect print, but you kind of get an idea. One, or horse away. Perfect. One. I really don't like this print, so let me let's change it. We can't really set it to be exit. Okay, I think exit. I think for viz, what we can do is print Horse away. Horse away. Okay, it's pretty accurate. Okay, let me Alright, so queen, good, good. Queen, good, 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 good. Diagonals are gonna be annoying to track, so this is the diagonal. This is I guess I just gotta assume it's correct, or I gotta do something about the diagonals. I mean, it looks correct. For some reason, it's not square in the print. Yeah, this is good. This is good. So I got one. Hey, for sure, all the rows are individual. All the columns are individual. And then we just need to check all this. So this is in the one row. I mean, yeah, looks good. Looks good. Looks good. Okay, so this guy. Sorry, I don't trust myself, so. Ah, perfect. And then this one's here. Yeah, this looks good. And this one's just above it. Usually they're like a night away. Night away, night away. Cool. This is an answer. God, this is... Alright, let's remove this actions thing. A few bugs that kind of delayed it. That's kind of how it goes. It's usually how it goes for me. So yeah, so this was really nice. I think if I were to do this in the future, I would make this a function. So I would refactor this to def get diag ri, and this would take a I, and then this would return an n, and this would return an p calls return, and then this equation. So this is just n minus 1 plus, and then it's, let's just call this row and row, because we just need the row, and then minus p calls row. So this is something I would have done, and then I would have switched this to, sorry, cis get diag r, and then here I would have given it 1. And same for this guy. So then I wouldn't have ran into this bug over here. And then you don't need this I here. This should pass unless I introduce a bug, which is very possible. I see it's just plenty screens. Yeah. The more isolated stuff you can make, the better. And I could have checked that. I think this validness, I could have isolated. You don't really need the values again. So I think this would have been worthwhile to drop into a function. And then this function, we have these inputs. Oh God. And then we just return the end. Right, and then we just make sure we have what we need. So we need p calls, p row, p calls, board, diag out. I think this is just the right way to do it, and then end. Sometimes you don't do it because you want to have everything kind of together, but then you can just do over here is valid queen equals is valid. Is valid queen, and we isolate the functions. So p row, p calls, board, diag L, diag R, and then here we do is valid, and then we don't have to worry too much. This diag R looks like something we can also move. And you just kind of run it. Okay, it's valid. Cool. This is like a little refactor, but you just kind of want to learn from your mistakes. Like, so here we want to do another one, def get diag L. Maybe we want this to go above it. And then here we want row p calls n. And same deal here. So here we can do, oh wait, it's this one. CI bracket. And then here we do p, and then we just need to fix it. So this is p row minus 1, because that was just a minus 1. And then return that. You actually don't need n for this one, so you don't want to ask for it. And that's just because you don't have to subtract by n. So then in this case, it's get diag L. And then here you just do p row minus 1. But now you get to go over here. And you get to change over here. Get diag L. P row p calls. And now that's a little cleaner too, and we can even check that in the future. Okay. Yeah, it's not bad to kind of change the convention. It avoids leaking stuff. Sometimes you just, by mistake, make like a bug. Like here I made a bug. goes. Yeah, cool. And moment of truth. I've never actually seen it, but I assume it'll work because it seems like the pattern means it will. And presto, runo. It worked. It's actually pretty fast.